Today's lecture is going to be devoted to a topic that you probably already know something about, namely the metric system of measurement. You probably know that scientists do not typically use English units like pounds or feet or inches when they're involved in whatever kind of work or research they might be doing. Instead, they use the metric system. Indeed, most of the world outside of the United States uses metric units for everyday quantities like distance, speed, weight, or temperature, for example. That's why if you are outside the United States, you will typically see distances posted in kilometers, kilometers, instead of miles. You will see temperatures expressed in degrees Celsius instead of degrees Fahrenheit, weights in grams or kilograms rather than ounces or pounds, and volumes in liters or milliliters instead of quarts and pints. The United States, for whatever reason, seems to lag behind in this regard. Now, when I introduce the metric system to my students, almost invariably, one or more students will say with total sincerity, "Boy, I hate that metric system. That is so difficult. The English system, our system, if you're living in the United States, that's easier." And they really believe this, probably for no better reason than the fact that they've grown up with these units for their entire lives of perhaps 15 or 16 years, so they are both familiar with them, and they may even have, although this is often actually not the case, a pretty good intuitive grasp of what an inch, a mile, a pound, a quart, or anything else really represents. But what is simpler about a system of measurement where you have to remember there are 12 inches to a foot, but 3 feet to a yard. Oh, and 5,280 feet to a mile. There's 2 pints to a quart, but there's 4 quarts to a gallon. There's 16 ounces to a pound. Oh, unless you're talking about fluid ounces, then there's 32 ounces to a quart, but those ounces have absolutely nothing to do with the other kind of ounces. Now, this to me is a very complicated system of measurement. What happened historically is that measurements were created in a very helter-skelter fashion, and they were often very imprecisely defined, often based on what seems today to be a rather odd choices. I mean, like the foot, literally being the length of a person's foot. I mean, that's hardly something that's very reproducible. By the late 1700s, it became increasingly clear that there was a great need for a system of measurements whose units were clearly defined, reproducible, and consistent across the world. Things had, in many cases, really gotten kind of ridiculous. I mean, for example, there was a unit called a grain, whose origin dated back many years. It was literally the weight of a grain of wheat. Now, in France, there were 9,216 grains to what was called a pound. Oh, but in England, there were 7,000 grains to a pound. Oh, that's unless you were an apothecary, what we would basically call a pharmacist today. Then there were only 5,760 grains to a pound. Well, you can imagine trying to conduct commerce between nations with such a messed up system of measurements. So in 1791, when I was just a little boy, a committee of the French Academy of Sciences decided to sit down and create a logical, coherent, and reproducible system of measurement. And by 1795, they had worked out that system of measurement, and we, of course, know it as the metric system of measurement. Now, the metric system has certain advantages. All fundamental units are defined in terms of things that are easily and accurately reproducible. For example, the meter was defined as 1/10,000,000th of the distance along a particular line or meridian between Dunkirk and Barcelona. But the actual standard was a platinum bar with polished ends. The length of that bar from end to end at a certain temperature was the official length of the meter. Prototypes were later made so other countries could have their own copy of the official meter. Later, this was changed to a platinum iridium bar with 2 graduation lines that were, by definition, 1 meter apart at 0 degrees Celsius. Secondly, they decided that all conversions within the system could be accomplished by simply moving a decimal point. things would either be 10 times larger or smaller, or 100 times larger or smaller, or whatever. And that's a whole lot simpler than 12 inches make a foot, but 3 feet make a yard, and 5,280 feet make a mile, etc., etc. So this became the International Metric System. Now, most students seem to believe that the system that was set up in the 1790s is still the one in existence today. But that isn't quite true. The system had flaws. There were some small errors made in setting up the original standards, and in addition, some of the standards were based upon objects that could be lost, damaged, stolen, or destroyed. For example, the bar that defines the meter, if that bar is stolen or damaged, we obviously have problems. As years passed, it became increasingly clear that the metric system could use some revisions and modifications. So an international conference on weights and measures was established. What emerged from this is what is now called the SI system. SI stands for Système International des Unités. A great French accent there, but we'll just call it the SI or metric system. This system is much like the original metric system, but there are some important differences. Here's one key difference. One great annoyance that had developed over the years that the metric system had been in use, was what you might call a proliferation of units. Units had been added and added and added until there often were several different units for measuring the same thing. We had ergs and we had joules for energy. Oh, and calories as well. We had newtons and dynes for force. We had angstroms, debye's, barns, ESUs, etc., etc. They decided they needed to clean up the system and cut down on the number of units. So they made a very interesting decision. They decided that they were going to determine exactly how many of what might be called fundamental units were actually needed to set up an entire system of weights and measures. And they were going to keep this number of fundamental units to an absolute minimum. Every other unit, and there are hundreds of units, every other unit was going to be derived from these fundamental units, which were called base units. Now, it has always fascinated me to think about how many fundamental units you would need. My intuition, honestly, is not very good here. I mean, I know the answer. But if I had to sit down and come up with an answer myself, I don't think I'd have much of a notion. How many base units do you need to derive every other possible unit in science? 2, 10, 25, maybe more? Although it actually took some time, it was eventually decided that 7 base units were needed. The base units cannot be derived from other units. They are fundamental units, very carefully defined. The derived units, while well defined, are not fundamental. They can be derived from the 7 base units. I'd like to make a comment here about the fundamental units. If you research the history of some of these units, you'll learn that some of the definitions of these units have actually undergone several revisions over the years. For example, as we said earlier, the meter was originally 1/10 millionth of the distance of a particular meridian on Earth. Then it was the length of a platinum bar. Later it was the distance between 2 marks on a platinum meridian bar. But like we said, bars can get lost or stolen, so an effort was made to base this length on something in nature that would never change. This led to the meter being defined as, and this always sounds kind of funny, 553,164.13 times the wavelength of a particular line in the spectrum of a particular cadmium atom. Whether that really makes any sense to you or not really doesn't matter. The point is simply that the wavelength thing will never change. So no matter what might ever happen, With this definition, scientists could always reproduce an accurate meter distance. Later, that was actually changed to 1,650,763.73 times a particular wavelength of a particular kind of krypton atom. That could be measured with even greater accuracy, evidently. Why all the changes? Well, the idea is to get the most accurately reproducible standard possible. Today, the definition of the meter is different again. The meter is now defined as the distance light travels in 1/299,792,458th of 1 second. That's a pretty short time, but light travels very, very fast. If you let a beam of light travel past you for that tiny fraction of a second, it will have traveled 1 meter by definition. There was, and still is, great effort being devoted to trying to establish the most accurately reproducible standards possible and to remove all of these definitions from anything that could be damaged, destroyed, or changed. Today, all but one of the base units is defined in a way that references something that cannot be changed or altered. For example, it is believed that the speed of light will never change. So by defining the meter as the distance light travels in a certain amount of time, the meter will for all times both remain the same and the distance will always be reproducible with great accuracy. The only exception is the kilogram. There still exists an actual kilogram kept at the International Bureau of Standards, with many countries having copies. This is considered to be a very bad thing, and research is still going on to try and find something in nature that would never change and that could be measured to an accuracy greater than the accuracy with which we can measure the mass of the standard kilogram. That goal had not yet been achieved when this video was made. The new system, of course, still retains the idea that all conversions within the system can be done in powers of 10. In other words, by moving a decimal point. So what are these 7 base units from which all other units can be derived? They decided they definitely need a fundamental unit of length. It is the meter. Here is a meter. Well, a replica of a meter, pretty close. They found that they did need a unit for mass. And the mass that they chose is the kilogram. Now, this actually bothered some scientists. In fact, it appears to have bothered the people who established the system. But they decided that because of the history behind this unit, they would leave it be. Now, you might ask, what's the problem? Well, the entire idea is that you have fundamental units and prefixes that are supposed to tell you how many or what fraction of a fundamental unit you have. There's a verbal problem here. If this is a fundamental unit, it shouldn't be called a kilo anything. One could argue that it should have been given a new name. The fact that when you say kilogram, there is an implication that the gram is the fundamental unit of mass, and you are taking 1,000 of them. But that's not the case. The kilogram, despite its name, is the fundamental unit of mass in the SI system. The fundamental unit of time is the second. The fundamental unit of temperature, believe it or not, is not degrees Celsius. Rather, it is something called the Kelvin. They found that they needed an amount of a substance, and the unit that they chose was the mole. All of these units can be abbreviated. Meter becomes M, kilogram becomes kg, second becomes just S, not SEC, as many people assume. Degrees Kelvin just becomes uppercase K, and mole becomes MOL. All very good, useful abbreviations, although I don't know, that mole abbreviation doesn't exactly save us gallons of ink. They found that they did need a unit for electric current and it's something called the ampere. And this one has always personally surprised me. They found that they did need a unit for how bright a light was, what they called luminous intensity. It happens to be called the candela. Now, of the 7 base units, you will probably encounter the first 5 in your chemistry class: meters, kilograms, seconds, kelvins, and moles. 6, if your course includes a unit on electrochemistry, the ampere. I don't know of any chemistry course that discusses candelas. Well, the idea now is that starting with these 7 fundamental units, all other units must be derived from them. Well, this leads to some interesting things. For example, suppose I said to you, what would be the correct SI unit for volume, the amount of space taken up by an object? Students will typically say, oh, I know that. We talked about that in the last lecture, the cubic centimeter. Au contraire, no. Now, you may like cubic centimeters. I like cubic centimeters. We will be using cubic centimeters throughout this entire course. But it is not the official derived SI unit of volume, because the whole philosophy of this system is that the 7 base units establish the system, and all other units must be derived from these 7 base units. So what would be the correct SI derived unit for volume? Well, volume is distance cubed. Therefore, if I follow this philosophy, the correct unit of volume has to be the fundamental unit of length, the meter, cubed. That's a big volume. A cubic meter would be a box 1 meter by 1 meter by 1 meter. Now, this is a pretty large volume. Aren't you glad that your lab equipment doesn't consist of beakers with volumes of cubic meters? Most people just assume that all scientists completely embrace the metric system. But in fact, there are many critics. And one common criticism is that many of the derived units are not of convenient size. And the cubic meter is certainly one of them. Of course, you can argue that just because the standard unit of volume is the cubic meter, that doesn't imply that you have to have large beakers in a lab. Just label them correctly. Okay. But that would mean that a beaker that is now so nicely labeled as being 250 milliliters would instead have to be labeled 0.00025 cubic meters. Now, which label do you like better? Well, because of this difficulty, what I call the inconvenient size of some of the units, you will still see a lot of what might be called practical units being retained. Included among these are things like milliliter, liter, gram, degrees Celsius, even millimeter of mercury, and many others. The committee actually decreed that certain of these units could be retained for a limited amount of time. To me, it actually appears that they are going to remain around for a very long time. Indeed, one could make an argument that the number of additional units that are being used every day may actually be growing, not shrinking. Once you understand the basic philosophy that every other unit has to be derived from the 7 base units, you now can run through several different kinds of units. For example, we've already discussed the cubic meter, the fundamental unit of volume, a cube, 1 meter on a side. We might ask, well, what would be the SI unit for area? Well, for simplicity, we might assume a square. Then area is a meter times a meter, or square meter. What would be the SI unit for the speed of an object? Now, that isn't trivial. If I asked you how to tell me how fast something was moving, you might say miles per hour if you lived in the United States, or perhaps kilometers per hour if you lived in Canada, for example. But if we use SI, it has to be the fundamental unit of length, the meter, divided by the fundamental unit of time, the second, or meters per second. When you take a physics class, and it's not important at this time that you understand what these terms mean, you'll discuss something called acceleration. how fast the speed of an object is changing. The number of meters per second the speed of an object is changing per second. So the SI unit comes out to be meters per second squared. It can get pretty involved. In physics, you'll talk about force. You'll learn that force equals mass times acceleration. Mass is measured in kilograms, acceleration in meters per second squared. So force turns out to be measured in units of kilogram meters per second squared. They give this unit a name, a Newton, and a symbol, uppercase N. When you get to energy, we'll talk about energy in chemistry. In physics, you learn that energy is force times distance. So it's newtons, which is the unit of force, times meters, which is the unit of distance. Since a newton is a kilogram meter per second squared, and we have to multiply it by another meter, you come up with units that truly begin to lose meaning. The unit of energy is a kilogram meter squared per second squared. Now, perhaps you can come to some intuitive meaning for this, but I think for most of us, that's pretty difficult. But we'll give it a name, the joule, named after a scientist named Prescott Joule. We always seem to feel better when we give something a name, and we'll give it a symbol, uppercase J. Now, you are not expected to understand all of these units that we just mentioned, but you should understand the philosophy that all other units must be derived from the 7 base units. So let's see if we've understood that. Take a few moments, stop the video if necessary, and try to answer this question. What would be the correct SI unit for density? Well, if you thought or yelled out, hey, I know that, we just talked about that in the last lecture, grams per cubic centimeter, that's what we used in the problems. Sorry. Intelligent, sensible answer, but not correct. Grams per cubic centimeter is a wonderful unit for density. That's the unit for density that we're going to use in this course. But it's not the SI unit, because the SI unit for density must be derived in terms of the 7 base units. Well, density is mass per volume. How much mass is contained in 1 unit of volume? Since the base unit for mass is kilograms, and the base unit for volume is the cubic meter, then the SI unit for density has to be kilograms per cubic meter. Now you might ask, why didn't you use that in the density lecture? Because no one is using kilograms per cubic meter, at least not around here. At one time, believe it or not, I was using a textbook that was actually published in Canada. And it did use kilograms per cubic meter, and that really was kind of inconvenient to me and my students. And I'll tell you why. In the last lecture, we talked about an object having a density of 3.45 grams per cubic centimeter. And we imagined holding a little cube in the palm of our hand, and we imagined 1 little cubic centimeter, and we imagined 3.45 grams. I think that was pretty easy to imagine. If you want to talk about this density in kilograms per cubic meter, it comes out to be 3,450 kilograms per cubic meter. Okay, we can probably imagine a cube 1 meter on a side, but can you really get a feeling for a mass of 3,450 kilograms? I mean, that's like over 7,000 pounds. I doubt it. Kilograms per cubic meter, while perfectly defined, is not a very convenient unit to come to grips with. And that's one reason why we tend to retain so many additional units. They are of convenient size for what we're talking about. Now, the SI system, just like the previous version, still has what are called prefixes. There are quite a few of them, I believe 20. If you are currently enrolled in chemistry, your teacher may or may not require you to memorize some or perhaps all of them. In my view, there are more prefixes than most students really need to know from memory. Although several of them are encountered so often, it probably would be a good idea to just know them rather than having to refer back to a chart of something all the time. I suspect you will learn many of them rather quickly, for no other reason than the fact that you will be seeing them used so often in problems. Going through the prefixes is kind of a fun intellectual exercise, so let's run through them once. What I mean by a prefix is the following. Suppose you have a base unit. Take whatever you want. Well, don't take the kilogram. Let's say it's a meter. That's 1 of whatever it is. Now, 1 is equal to 10 to the 0 power. Be sure to remember that. Occasionally, a student will think 1 is 10 to the first power, but 10 to the first power is 10, not 1. So 0 becomes the exponent of the base unit. So what if you had a large number of something? Well, then we put a prefix in front of the symbol for the thing telling us how large it is. Here are the prefixes that are often used when you have large numbers of whatever you are talking about. I've highlighted the ones that I personally think are the most useful for you to know. The largest defined prefix is 10 to the 24th. It's called yada and given the symbol y. I don't know why they didn't call it lotta. I thought that would have been the greatest name for the biggest prefix. I got a lot of meters, but they called it yada. 10 to the 21st is called a zeta, capital Z. 10 to the 18th, an exa, capital E. 10 to the 15th, peta, capital P. 10 to the 12th, tera, capital T. 10 to the 9th, we call it giga. That actually isn't the correct pronunciation, but everybody calls it giga, so we will call it giga. You know, gigahertz on a computer, capital G. 10 to the 6th is a mega, capital M. 10 to the 3rd is kilo, and here they use a lowercase k. 10 to the 2nd, hecto, lowercase h. And 10 to the 1st, deca, which has a 2-letter symbol, the only one, da. You notice that we do not have prefixes for every power of 10. For example, we do not have a prefix for 10 to the 4th, although at one time such a prefix actually did exist. We also don't have prefixes for 10 to the 5th or 10 to the 7th, or many other possibilities. There really isn't much of a need for them, and you're probably glad since it means there's going to be fewer to learn. There are prefixes for 10 to the 1st, 2nd, and 3rd, and after that they jump by powers of 3. If you have less than one of your base unit, if you have a fraction of your base unit, the prefixes are the following. 10 to the minus 1 is called a deci, symbol is lowercase d. 10 to the minus 2nd, centi, c. 10 to the minus 3rd, milli, m. 10 to the minus 6 micro. They actually use a Greek letter mu here. 10 to the minus 9th, nano, lowercase n. 10 to the minus 12 pico, p. 10 to the minus 15th, femto, f. 10 to the minus 18th, atto, a. 10 to the minus 21st, zepto, z. And 10 to the minus 24th, yocto, y. If you ever heard of the Marx Brothers, somehow the last 2 prefixes remind me of Chico, Harpo, Zeppo, and Yocto. Now you may think that this is a rather complete introduction to the metric or SI system of measurement. Hardly. I am completely serious when I say that it would be quite possible to devote this entire series of lectures, all 36, to the history of measurement and the SI system. There are literally several dozen different defined quantities, along with all kinds of exceptions and qualifications, etc. If your teacher ever asks you to prepare some kind of a extra report, maybe for extra credit or something, this could provide you with an excellent topic. Now, one of the most common tasks required in many high school chemistry courses is the ability to convert from one unit to another, both within the metric system and between the metric system and the English system of measurements. In the next lecture, we will take a look at various ways in which this can be done.